Very good morning, Professor Platzer, and good afternoon for Sri Lankan audience. Uh, uh, Today we are going to start our fourth webinar, which is organized by EUSL-Energy project and also SLAS Section C and the Department of Mechanical Engineering, the Open University of Sri Lanka. Let me introduce Professor Platzer briefly. I hope all of the audience are familiar with him because we shared his extensive biography using Learnify link. So I hope all of have been very familiar with Professor Platzer now. Professor Platzer got his got his PhD, Doctor of Technical Science, from Technical University of Vienna, Austria, and he so far he has 50 years of experience in aeronautics, and in the last 15 to 20 years he focused more into aeronautics. And presently, Professor is adjunct professor at Department of Mechanical and Aerospace Engineering, University of California, Davis, US, and also he is the Distinguished Professor Emeritus, Naval Postgraduate School in California. And he also serves as the editor of the International Review Journal, Progress in Aerospace Science. He has extensively published, including 3 US patents, and also he's got honored with Distinguished Professor Award from Naval Postgraduate School, and also elected as the Fellow of American Institute of Aeronautics. And Professor Platzer is going to give a lecture on a very interesting concept, which called energy ship. It's about production of hydrogen from wind over water using energy ship concept. Actually, this is quite interesting concept for us, for most of us, since we are focused on renewable energy. So without much taking time, I will hand over the audience to the Professor Platzer. Professor, audience is yours.
Thank you very much for the kind introduction, and thank you for the invitation to give this lecture. I'm very honored that I was invited. What I would like to present today is essentially talk about 3 points I would like to get across. The first one is I would like to draw attention to the existential threat posed by the onset of irreversible climate change if the transition from fossil-based to emission-free global power generation cannot be accomplished before mid-century. The second point is that I would like to motivate my engineering colleagues to face up to this threat and to participate in the planning and execution of what I would like to call an energy Apollo project. That comes natural for me because as you probably have seen, I have participated in the original Apollo project. Well, that was 70 years ago. No, it was 60 years ago. I'm sorry to admit. And of course, I also would like to explain, at least that is my view, that only an emergency action has a chance for success to switch to renewable energy production. So here we are on spaceship Earth, and we have to ask ourselves whether the air conditioning system, as I would like to call it, of spaceship Earth is failing. And I think there are plenty of warning signals. We all know that the CO2 level is increasing. The sea level as such is increasing. The Arctic ice is decreasing. Temperature is increasing, and there are many other signs that we are having considerable problems. So let us first look at the big picture, what I would like to call the big picture, before we go into more details. Here you see the history of the population of our planet. And It, of course, stayed well below 1 billion until about 1830. And the next 100 years, it increased by the 1930s to 2 billion. Well, I have to admit, that was the time when I was born. And look what happened in my lifetime. It quadrupled. It's now approaching 8 billion. So obviously that means that the energy needs of these 8 billion people are enormous. And not only that, a good part of the population of the Earth has had the good luck of increasing its standard of living, which of course meant to increase the energy demand and the energy used by all these people. So that accounts, of course, for our energy problem. Now, look also at this picture here. Again, you see the same thing, an explosive growth in just 70 years. And whoever drew this graph, of course, felt that one of these days we have to stop. Clearly, we cannot have a situation where we have another quadrupling. If we have now 8 billion, in another 70 years or so, we might have 30 billion. And that is hardly conceivable. So it was extrapolated here that we might stop at around 10 or 11 billion, or maybe even less than that, and then keep it constant. Now, what actually will happen, of course, is anybody's guess. But again, the main message, of course, from these two graphs is that we have had an explosive growth. And that has problems, that has generated problems as far as climate change is concerned. So let's quickly look at the empirical evidence which we have so far. And of course, the main problem here is, as we now all know, and I didn't know for many, many years and didn't pay any attention, and that is the critical role of carbon dioxide. For instance, I never knew for a long time that if there were no carbon dioxide in our atmosphere, we would have a mean temperature of minus 18 degrees Celsius, and the whole globe would be covered with ice. So carbon dioxide is absolutely critical for the existence of humans. Now, of course, carbon dioxide, as we also know, is a tiny part of the total atmosphere. And it is amazing that this small amount of carbon dioxide has such a critical role. Now, on the other hand, of course, if you increase the carbon dioxide too much, then you generate this greenhouse effect, meaning that the carbon dioxide is preventing the reflection of the infrared radiation due to the warming of the Earth. It comes in at a certain radiation level and it goes out at another one, at a lower one. And the carbon dioxide prevents the radiating out of this radiation. And that causes the increase in the temperature. That's basically the problem, that the carbon dioxide, which as already indicated, is absolutely vital for our existence, can hurt us enormously if we get too much of it. And here's the problem. Here is the decay rate of the carbon dioxide. And as you can see from the upper picture, in about 100 years, there is still 35% of the carbon dioxide which is emitted today in the atmosphere. And if you go out 1,000 years, then still 20% will be in the atmosphere. So that stuff stays there, unfortunately, and that is a real problem. And now take a look at this picture, which is a very important one in my view. It shows you the measured carbon dioxide over the last 800,000 years. And as you can see, it fluctuated between values of 160, 180 parts per million. As I said, it's a very small amount to begin with. And it never exceeded a level of 300 until about 1950. And then it really started to explode. And as you can see, On the right-hand side, it exploded enormously over the last 70 years, and it currently holds at almost close to 420. And if it goes on like that, if you let it go rise to something like 500 or even 600, that will be truly catastrophic. So we need to prevent this by all means. Now, if you just look at the last 70 years, that is another excellent measurement. It's well known, it's well established. There is no question about the reality of this. And again, you see the increase since 1954, for instance, from about 315 all the way up to now almost 420. So it is there, it is occurring, and it continues to increase. And of course, we need to bend it around. We need to bend it down to zero. And hopefully we can do that by mid-century, so by 2050, we ought to bring it down. The big question, of course, is how can we do this? Another thing, of course, is we know the measured sea level, and it increases and increases, right? So you see here, at the rate of increase gets greater in recent years. And so if, again, this goes on, then a number of problems occur, in particular in low-lying countries such as Bangladesh, for instance. So that needs to stop. You get information about that, for instance, by a book by Professor Ward at the University of Washington. And the projection is that the sea level will rise by 3 to 5 feet, that is by 1 or 2 meters by 2100. And that is within the lifetime of a young person these days, right? So it's a problem. Additional evidence, of course, is increasing acidification of the ocean, retreat of the glaciers, the thawing of the permafrost in Alaska and in Siberia, an increase in frequency and magnitude of the storms we are experiencing, in particular now in the United States, an increase in the mean temperature. And if you pay attention, of course, you're well aware of this. Now, additional information, of course, can be obtained in quite a number of sources. I would refer you to the reports of the US Academies of Science and Engineering, the National Science Foundation, and in particular also the reports of the Intergovernmental Panel on Climate Change under the supervision of the United Nations. So the question is, how serious is the global warming problem? I refer you in particular to the warning put out already for the last 40 years by the former director of NASA Goddard Space Center in New York, James Hansen, who is well known in this field, and he has published a report together with many other authors. I refer you to here that was published in 2013. So there is another much more dangerous phenomenon, however. You might say, well, if we can change it around, let's increase it somewhat more, and we can bring it down one of these days, and then everything will be fine. Unfortunately, that is absolutely not the case. And that is perhaps much less known and appreciated by many people. Namely, there's the phenomenon of irreversible climate change. There are indeed tipping points, and once you get let it go past these tipping points, then you have an unstoppable melting of the ice on our planet. And that means the change from a white area reflecting back radiation to blue and brown. And that means more warming, and that means more melting, and this goes on and cannot be stopped by any technical means anymore. So that is a true problem. And that has been analyzed by quite a number of people, for instance, by colleagues at the University of California, Davis, and this article already put out in 2012. And in particular, I refer you to 2 recent books by Anthony Barnowski at Stanford University, who details this in great detail. So the information is there. You only need to look at it, and it is very dangerous indeed. And that has caused the United Nations Secretary General, Antonio Guterres, to put out a warning and saying that the world is facing an emergency and that we need to transition to renewable energy by no later than 2050. So he has declared this emergency, and it has been joined by 38 governments already. And of course, recently, President Biden of the United States has also joined this declaration. So it is a very serious problem. It is truly an emergency. Not everybody will agree, but I would like to emphasize that the evidence is absolutely there and cannot be ignored. So the warning is the world will become irreversibly uninhabitable unless fossil-based power generation is replaced by renewable power generation no later than 2050. So the big question is, can we do this? Is this technically feasible? And of course, another question is it politically feasible? I will at first, of course, address mostly the technical question and then talk a little bit also about the political problem. But before we do that, let us not forget that by we, I mean mostly the engineering community, we can look back at enormous past accomplishments. And they can be summarized in terms of the energy use which we have available. And it has increased by an order of magnitude. Now, Professor David McKay of Cambridge University has put out a very nice book, which is available on the internet for free. And he measures everything in kilowatt hours. So I think that is a very good measure because we all pay our electricity bill in kilowatt hours. And he's saying, and he can prove, of course, that the energy increase used in the developed countries increased largely over the last 100 years or 200 years from about 20 to 200, and in some countries even more, to 300 and even 400 kilowatt hours per person per day. Not everybody participates in it yet, unfortunately, but that of course accounts for the energy demand which we have. That is a picture which I took from his book, and you see here in the developed countries, you have a power consumption, an energy consumption, I should say, per person per day, which, for instance, is around 100 to 150, mostly in Europe. It approaches 200 in the United States, and in places where it's very cold, like in Canada, it even approaches something like 350. And where it's very warm, in Oman, for instance, or Abu Dhabi or whatever, it has about the same value. So that means, of course, energy consumption has gone up. And we owe that accomplishment, which is a major, incredible accomplishment if you think about it. We have, those of us who are lucky enough, we have experienced an incredible increase in our standard of living. And I just remind you, of course, the father of all this is Isaac Newton. And I put these dates here because it's also remarkable that all this occurred only over the last 300 and 400 years. Right? James Watt showed us how to convert coal into usable energy. And that is only 300 years ago. And Nicholas Otto in Germany, of course, showed us how to convert oil into usable energy. So these are accomplishments we should not forget. And they should remind us that these tremendous increases should give us hope that we can also do something about this threatening climate change. So I would like to summarize this. Mechanical and also aerospace engineering produced an incredible standard of living. I sometimes put it like this, and we literally conquered space and time. What do I mean by this? Well, we can fly to any point on the Earth within 24 hours. So we conquered space, and we also conquered time, because after we have been able to put satellites into orbit. Now the communication system is at the point where, as you can see right now, I can talk to you over a very large distance, and we have instantaneous communication. If you think about that, that is absolutely astonishing. I would never have thought when I was a child that anything like that would be possible. Unfortunately, as we now also realize, it is now threatening the survival of humankind. And so we have to ask ourselves whether we can provide ourselves with emission-free power generation. That, of course, is the question. I already mentioned James Hansen. He put out a book in 2009, and we call it Storms of My Grandchildren. As a meteorologist, of course, he was very concerned about that increase in storms. And there's another interesting book. It refers to the Apollo program by Jay Inslee, who currently is a governor of the state of Washington. And he calls it Apollo's Fire, Igniting America's Clean Energy Economy. He puts that book out in 2008. And then, of course, you are probably familiar with the books by former Vice President Al Gore. And so a quote here, for instance, from Inslee. He says in this book, opportunity is best found in crisis. Boldness is required. Tinkering at the edges did not put a man on the moon. We must reject the tyranny of the present. But unfortunately, also finished his book by saying, as far as he can see, there are no silver bullets. I repeat that. There are no silver bullets. That was the opinion, and probably still the opinion of far too many people. That there are no silver bullets, that gives the impression that we engineers are not able to turn this around. And that, I think, is a challenge for us engineers to convince everybody, to convince our fellow citizens on this earth that this is probably not true. At least it is my position that this is not true. However, let me quote another well-known gentleman, Professor Václav Smil, who has published many books on energy. And he's saying that energy transitions have been and will continue to be inherently prolonged affairs, particularly in large nations whose high levels of per capita energy use and whose massive and expensive infrastructures make it impossible to greatly accelerate their progress, even if we were to resort to some highly effective interventions. Now, this is a rather depressing message, isn't it? And the evidence actually shows that he is largely correct. These energy transitions, let's say from coal to oil and then from oil to natural gas, have taken a considerable time. Well, something like 50 to 100 years, but we have to do this in 30 years or less. So the real question that we have to ask ourselves is this indeed possible to do this? Now, my counter argument is that Smil, of course, is basing it on his evidence, and the evidence refers to largely peaceful developments, and there the profit motive plays a major role. In fact, it plays a critical role. But then we also experienced times when we had emergencies. Now, I myself experienced 2 emergencies, so my views are, of course, influenced by my personal experiences. I guess everybody's experience is always influenced by personal experience. And I experienced World War II, admittedly, as a child. I didn't understand exactly what was going on, but I experienced World War II. That truly was an emergency. And then I had the good luck of participating in the Apollo program, and that, as far as America was concerned, was also an emergency. And let me remind you, let's go back to World War I. The first airplane, of course, was produced by the Wright brothers in 2003. Now, 15 years later, by the end of World War I, 200,000 airplanes had been produced. So that is quite a bit. Then let's go to World War II. It took only 5 years to produce the first jet-propelled aircraft in World War II. It first flew in 1939, and by 1944, the first operational jet fighter was put in the air. And that was a Messerschmitt 262. And it took only another 15 years to switch to jet-propelled commercial aircraft. Right? The Comet, the British Comet, was the first such aircraft, and that introduced the possibility. And we all enjoy it now and take it for granted that we fly by jet-propelled aircraft and not by propeller airplanes, which I first did when I came to the United States. And that is a very pleasant ride. So we have accomplished this as a result, again, of another emergency. And then let me also remind you that the first supersonic rocket, of course, was a V2, and that took only 10 years to develop. It became operational in 1944, and only 13 years later, such a rocket, the successor to the V2, developed in Russia, of course, put the Sputnik into orbit, and then was followed in the United States only a few months later. And of course, 12 years later, astronauts landed on the moon. Though these are things which were accomplished in something like 10, 15, 20 years. And that should give us hope that if we really put our minds to it, that we should be able to also do something about the climate change problem. So that is my observation. World War II demonstrated, however, and that is the other point which I would like to make, the Germans developed, and they were in the two emergency, right? They developed new technology. They developed the jet aircraft, much faster aircraft than the Americans were able to put into the air. And they also developed rockets. They thought they could win by going to new technology. I would suggest that this is the wrong approach. The correct approach is what the Americans did, namely they used readily available hardware, of course military hardware I'm talking about, plenty of airplanes, trucks, tanks, you name it, ships, and mass produce them. And so my opinion is that one should not count on the development of new technologies. One often hears these days that maybe we have to wait for breakthroughs in energy technology, and that will save us. Well, we only have 30 years left, I keep telling you. And if we bank on new technologies, as the Germans did in World War II, that is probably not good enough. That will not come fast enough. So we need to look for technologies which are readily available. And I also had an experience on the Apollo project. It is not well known that readily available hardware was used in order to start the Apollo project. Namely, there were Jupiter missiles which were developed by the von Braun team. I know about this. And these Jupiter missiles became obsolete, although the United States Army had plenty of tanks and engines. And so Werner von Braun suggested that let's just bundle 8 tanks and engines readily available, and that would be the first stage of Saturn I. And so that increased the available thrust from about 200,000 all the way to 1.5 million pounds in a very, very short period of time. And that Saturn I was designed and built in-house to save time and cost. And that ultimately, of course, was followed by Saturn V, and the rest is history, right? So the lessons here is use available technology if at all possible. And that is the lesson from Apollo. So what can we do in order to do something in time about the climate change problem? So let me concentrate on that now. Obviously, we have to ask ourselves, where are the available energy resources? And of course, I'm talking about renewable energy resources. And I started thinking about that something like 15 years ago. And it struck me that we were all talking about building wind turbines and solar panels, et cetera, et cetera. And we took it for granted that, of course, these things are heavy. In particular, the wind turbines became very large and very heavy. Well, that naturally suggested that you had to have a firm foundation, and that, of course, is provided by land. And nobody talked or dared to talk about the fact that we have strong winds over the oceans. And of course, we are all aware that 70% of our globe is covered by water. And so we have plenty of wind power that is available, potentially available for conversion into usable energy. So from an engineering point of view, in my view, the obvious question is that we have to answer the question, is it possible to tap into this, what I would call essentially an inexhaustible energy resource? And it certainly is worthwhile to think about that question. Now, when I started thinking about it, I felt, well, that's probably, the answer to that is probably negative. Somebody would have done this a long time ago. Would have felt, well, this is the obvious thing to do. And the conclusion probably was it's much too difficult and it cannot be done. So that's the answer which I expected I would also come out with, in spite of the fact, of course, our vast ocean areas with strong year-round winds, which offer a much higher capacity factor. Right? That means they are available for most of the year than the wind resources that are available on land or close to land, offshore. So the true question is there a practical way to tap into this vast power source? So I summarize here, wind over water represents the largest as yet unexploited energy reservoir on our planet. And wind over water energy exceeds the foreseeable global energy demand by an order of magnitude. If you want numbers, we're talking in terms of power. Total global demand is somewhere in the order currently of 19 terawatt, a huge number, of course. And it's projected to go up by 2050 to something like 29. But the amount of power available in the ocean winds is something like 200 terawatt. So it's an order of magnitude higher. So we will have plenty of power if we can convert this ocean wind power into usable power. So that is what we should be doing, and we should be asking ourselves whether that is possible. So take a look at this picture here. In both winter and summer, in particular in the red areas, you have wind speeds in the order of 10 meters per second and higher. And they persist, at least in these areas, for most of the year. And these, of course, are vast areas. And we ought to be able to take advantage of this kind of wind power. And that leads me to what I call a new discipline. So we know about aeronautical engineering, and we know about hydronautical engineering, and we know about power engineering. And if you work in one of these three disciplines, you essentially stay in this discipline, and you have no reason to get out of this discipline. Well, that's the way it is, because that is a difficult enough area to absorb in terms of skills and knowledge. But in my view, you have to start thinking in terms of emerging of these three disciplines, and therefore I call it aeronautical power engineering. And what does that mean? What does it imply? Well, if you look at this from a new point of view, then you have to ask yourself, should we be able to drop the assumption that only stationary devices, wind turbines, power plants, large heavy power plants, that this assumption should be dropped for wind or water energy conversion? And we also should ask ourselves whether when we do aeronautical power engineering, that this requires a further dropping of the assumption that only one single medium, either air or water, can be considered for energy conversion at any given time. So the dropping of these two assumptions is very, very important. So we have to think about this problem, in my view, differently. And of course, as is well known, if you always start with the same assumption, you shouldn't be surprised that you end up with the same result. So as long as you don't drop these assumptions, which we currently have been making all the time, we of course will not make any progress and venture out into new areas. So we need to be aware of the fact that these assumptions need to be dropped. So how do you do this? And that leads to what I think is what I call the energy ship concept. A number of other people are now calling it that. A number of other people have become interested in this concept, which of course makes me very happy indeed. So if you say, well, we need to go out and look for larger wind speeds, then of course the next logical step was to go to floating wind turbines. And that is indeed something that is now being considered. So instead of offshore wind turbines, let's go to floating wind turbines. So let's go out a few miles off the coast because there we find stronger winds. And let's do that. And as a matter of fact, just a few miles south from here, we are now starting a project of that where we will apparently develop California will develop a floating wind turbine farm. What is the wind speed? The average wind speed which will be available? Well, it is 4 meters per second. Well, it's actually quite low, right? So the next logical step, of course, is why should we stop at the edge of the ocean? And why don't we go further out into the ocean? Can we do that? And that, of course, leads to the question, well, we have done this for thousands of years, right? We know how to build sailing ships. That started some 5,000 years ago with the Phoenicians, and that had been developed to a very high state of the art indeed, right? And until about the 1900s, everything was done, commerce and also, of course, military operations were done with sailing ships. So obviously, these sailing ships are available. The question is, can these sailing ships be used for power generation? So that is, of course, the question, can this be done? So on floating wind turbines, of course, you have a huge turbine which you have to stabilize, and it presents an enormous surface area to the storms. And if you have a real strong storm, then you have a real big problem. Not so on sailing ships. And that was the beauty of sailing ships, recognized very, very early on, of course, that you can do something about the area which you're exposed to the wind. You can take down those sails quickly, and you can survive storms. And that is the key, right? So you can use these sailing ships. You can make them survivable by using sails which you can take down if needed. And you can have a wind capture area which is equally large, and it all probability has to be larger than what you have as capture area for the wind turbines. And you propel your sailing ship, and now you have a certain speed, and this speed can certainly be higher than 4 meters per second. It can be something like, in our analysis, we start with the assumption that it can be somewhere between 5 meters per second all the way up to 10 meters per second. And so if you put a hydrokinetic turbine on your sailing ship, then you can, of course, generate electricity on your sailing ship. And you have to realize also at the same time that hydrokinetic turbine, of course, operates in water. Density of water is 800 times larger than the density of air. As a result, the hydrokinetic turbine is an order of magnitude smaller than the wind turbine. And though you have a relatively small turbine which you can put on your sailing ship. And now, of course, you have to ask yourself, what are you going to do with a lot of electricity which is being generated on your sailing ship, and you are in the middle of the ocean, let's say somewhere in the South Pacific, and what are you going to do with that electricity? So here it is. Here is the basic concept. Here is your sailing ship. And here is your turbine. Look first at the upper picture, and you generate electricity. And how would you store this electricity? Well, the obvious answer is we have electric batteries. Let's store it in batteries. And then let's bring it back to shore. Well, probably not a feasible idea if you're in the middle of the ocean. It is a feasible idea if you're operating close to the ocean, close to the coast, sorry, and you bring those batteries back periodically, let's say within a few days every time. And so you go back and forth between the harbor, unload your batteries, load discharge batteries, charge them, and do this constantly. That is one way of looking at it. And the other way of looking at it is you use the electricity, and that is the lower picture, and you put that electricity into an electrolyzer. Yes, you have first you have to actually desalinate your seawater. Put that into an electrolyzer. Now you split the water into hydrogen and oxygen. Let's forget about the oxygen for the moment. And now you store the hydrogen by compressing it. It's of course the lightest element, takes up a lot of volume, so you at least have to compress it, if not liquefy it. And now you have hydrogen tanks on your energy ship. And what do you do with that? Well, you have to bring it back by separate ships, in all likelihood, by tankers, bring it back to shore. And now you can use this hydrogen directly for cooking and heating purposes, or you put the hydrogen, the compressed hydrogen, into your hydrogen fuel cell vehicle. Some of them are already operating, as you well know. Or you reconvert it into electricity in special power plants or in fuel cells. And when you do that, you get an extra bonus. You get what you might incorrectly call as a waste product, namely you get potable water. So that is the hydrogen production sequence, which I mostly would like to talk about. So to summarize, the basic scheme is use sailing ships, a well-developed technology. And remember what I said, well, we should use readily available technology. Sailing ships or sailboats are largely used these days or regarded as for luxury purposes or for sports events, for competitions such as the America's Cup, and not anymore for commercial purposes, but that, in my view, is a mistake. So the energy ship provides a turbine inflow speed of 5 to 10 meters per second. It can be scaled up. Large sailing ships have been built in the past, all the way up to 7,000 square meters of sail area. This has been done. Though that can be done again, obviously. These sailing ships can be operated autonomously. And that's a very important point. I struggled with that point for quite a while because the argument, which of course I received, and that is a valid argument, is these sailing ships, if you have to have crews on them, you would have to have at least 20 such people on it. And then it becomes enormously expensive and uneconomic. Well, nowadays, of course, everybody is talking about autonomous cars, autonomous ships, autonomous drones, autonomous, even autonomous planes, right? That is not a problem anymore. This certainly can be done. And to have autonomous small boats is already done. It's already done by the military services and also commercially. So the energy ship, of course, can deliver either battery stored electrical energy or compressed or liquefied hydrogen. And while the output per sailing ship probably in our analysis is not more than 3 megawatt, although there are proposals to be able to increase this to something like 30 megawatt, as I will explain. It certainly will require, and some people may argue about the feasibility of that, if you want to generate terawatts of power, then of course you will need millions of energy ships. Well, is that feasible? Well, it depends on how urgent the need is, right? Go back to World War II. Right? These things were done, the ships and the tanks and the airplanes were built in just a few years. So yes, you can build quite a number of energy ships if you really want to. This is not a problem which is technically impossible. We have my colleague Sagar Klein at UC Davis and I have published a book on that, where you find many more details. So I have to refer to that for a more detailed discussion. But let me go through the main parameters quickly. And I have only about 15 minutes, so I think I can do that. So obviously an important parameter is the wind speed. As already said, wind speeds are available on the oceans. So, high wind speeds are available. And of course, that means that we can drive our ship at considerable speed. In fact, nowadays, we can drive the ship at speeds which exceeds the wind speed by a factor of 2, or 2.5, or even 3, as I will explain, right? And of course, on normal sailing ships are displacement boats. They generate a lot of drag. And your turbine, of course, by necessity generates drag. So you have to overcome this drag with a sufficient sail area in order to be able to keep your sailing ship operating at a sufficient speed. So an important parameter, of course, is how much drag does your ship generate? And what is therefore the wetted area? Drag is dependent on the total wetted area. And so it is clear you need to reduce the wetted area. And of course, you have to also put up with the drag that is generated by the turbine, and you cannot avoid that. There is a minimum amount of drag which is necessary if you want to generate power. So are such boats available? Well, just look at the America Cup boats. Here's an example. How fast can they sail? Well, we know, and you can see that on YouTube and on many other locations. You can see them in San Francisco, of course. They can sail at a speed twice the wind speed and more. And they are not using the normal display. They are not normal displacement boats, but they, of course, use hydrofoils in order to minimize the wetted area. So here's an example of such a boat. This is a beautiful example, and that should delight every engineer, in particular, of course, aerospace engineers and aeronautical engineers. How do you do this most efficiently? And of course, now the solution is you have to have these very sophisticated hydrofoils. And though that is a very challenging, very interesting area, aerospace engineers in particular like such challenges, so that is wonderful from my point of view. And can you already buy such boats for your own use? Yes, indeed, there are such boats available. Here's another example. And look again at the hydrofoils. Right? So yes, these things can be done, are already available. And so basically the scheme, I'm suggesting the ultimate energy ship, not immediately, probably at first you would use displacement boats, is a hydrofoil boat of this type here, which as you can see has a hydrokinetic turbine and of course has to have a sufficiently large sail area. All this has to be analyzed, and we have done this to some considerable extent. So let me remind you again why offshore wind power in terms of offshore wind turbines is not a good idea. Power output, of course, is proportional to the cube of the wind speed. And this has motivated the construction now of offshore wind turbines that are anchored to the seafloor, or more recently, the construction of floating wind turbines. But floating wind turbines, first of all, are still limited to very close to the coast. And they are limited in wind speed. The capacity factor is limited. So there are time periods where you have not enough wind, like for instance, close to where they are now trying to build such a floating wind turbine farm. And they, of course, pose severe challenges to survive storms. And that, to a large extent, goes away with energy ships, because the advantages are these energy ships can access much higher wind speeds. Energy ship can avoid severe storms. We have enough meteorological information available at any given time to sail away from severe storms. The energy ship can achieve a much higher capacity factor, as I showed you, right? These wind areas in certain parts of the oceans are available for most of the time. And another important point is the energy ship can operate autonomously. And the energy ship can extract both hydrogen and CO2 to produce even synthetic aviation fuel. It takes a lot of energy to produce CO2, to extract CO2. Work like that is going on by the United States Naval Research Laboratory. So you can even think of using such fuel for propelling ships and cars, and in particular airplanes. In that case, you don't need to change the airplane itself, and also not the infrastructure. And that is probably the first thing that ought to be done in order to make aircraft operations sustainable. And it's not renewable. You put out still you burn the fuel, and so that stays in the atmosphere, but you recover it, you take it back out of the ocean. And that is what we call, of course, sustainable. So the ship speed is determined by the hydrodynamic drag coefficient caused by the wetted area, or it said so, right? And we ought to go to, in my view, from displacement boats to hydrofoil boats. And of course, the ship speed is determined by the turbine drag. And therefore, the amount of power which you can extract by the turbine is very important. I've had the good luck of working together with a colleague at the Technical University of Darmstadt on that. He had a PhD student who analyzed this in some detail using systems analysis code, which he had developed, optimal systems code. And that is published in the Journal of Energy, where you can find more details about this. So to just give you a few results, if you sail at a wind speed of 10 meters per second in what I call the beam reaching mode, most of you probably know what that is, and you have a boat with 50 square meters of sail area, can produce 13 kilowatt. If you do this with 3,200 square meters sail area, you can produce something like 1 megawatt. And what is beam reaching? Well, as you also know, right, you have to have the wind coming essentially at a right angle to the direction of your boat. So that's the optimal wind angle, something like that. It's not exactly 90 degrees, but I don't go into those details here. You find them in the publications which I just mentioned. So what are we doing right now? Just I want to give you a quick overview of that. We will acquire a sailboat that we can operate in the displacement mode, in the semi-foiling mode, and the full foiling mode. And we design and manufacture a hydrokinetic turbine, determine the power output for various operating conditions, explore improvements due to semi-foiling and full foiling. I work with a colleague in Germany at the University of Coburg on the hydrokinetic turbine. And we have analyzed now a sail at the Naval Postgraduate School with colleagues. And we published a paper on that, on so-called twin skin sails, which have the advantage of a rigid wing sail, but not its disadvantage, and have a better characteristics than pure closed sails. Others are working on this. I found a reference to a Japanese hydrogen production project. Japan's Mitsui OSK lines and the University of Tokyo are at the moment testing yacht-sized energy ships, and will go on to larger ships apparently in the near future. Here is such an example which I found, and that one, of course, would have, in this case, 24 sails, and might put out something like 30 megawatt, which of course would reduce the number of energy ships needed in order to cover the global energy demand by a factor of 10. And there are current tests going on at the University of Nantes, I'm aware of and in contact with. They have already tested a small energy boat. So the advantages are wind power is freely accessible. It yields a storable energy source, particularly hydrogen. It yields potable water. And of course, the energy source is essentially inexhaustible. So as I already said, millions of such energy ships should make a considerable difference. Now, there's an interesting proposal which was made by colleagues at Stanford University in 2009. They called it the wind, water, solar proposal. And that is all land-based. Now look at this. That was proposed by Jacobson at Stanford and DeLuca at UC Davis. And they proposed to build 4 million on and offshore 5 megawatt wind turbines, plenty of PV systems, concentrated solar power plants, 49,000 and 40,000 PV power plants, et cetera, and a few other things. And they are working very diligently on it. But as you have seen, unfortunately, the friction to do this is very large. And the progress is very slow, and CO2 emissions have not come down. And why is that so? Well, I call it that is because of Newton's first law. There is, of course, an incredible amount of momentum that has built up the infrastructure. All the laws, all the regulations, and the special interests, they all impede the rapid transition. Emission-free energy production is perfectly understandable. This is why Vaclav Smil is saying, well, it cannot be done in a short period of time. Now, the other thing, of course, which is very important is Newton's second law applied to this problem, and that is, if you want to make change, you need a large force, right, in order to change direction. And that, of course, is what is needed here. So enough people need to put pressure on the powers to be, on the governments and all the people who are saying that it cannot be done. And I appeal in particular to the young people, and they have the most interest in this. They need to put the pressure on all sorts of people to make sure that this is indeed a real dangerous problem for them, and something needs to be done. And my view is, as a matter of fact, it can be done. So I refer you to the only book put out by an engineering professor I'm aware of, the University of Notre Dame. And he called it a wicked problem. And he's saying reducing emissions will require all hands on deck. As individuals, organizations, and governments, the entire global community must be part of the solution. Will this story have a happy ending? Will the effects of global warming be manageable? At this time, there are no answers to these questions. But what can be said is that through its action or inaction, humankind will determine its own destiny. I am surprised that Professor Inker is taking this attitude. As an engineer, we should be proposing solutions. And he has not done this, so I'm appealing to all my engineering colleagues, let's get going with this problem. It can be done. Now, another book I would refer to is by UCLA professor, history professor Jared Diamond. His book is called Collapse: How Societies Choose to Fail or Succeed. And this has been a bestseller. It's still available, I think, everywhere. And in this book, he shows in these days, I have shown why the Easter Islanders, the classic Maya, and other past societies have collapsed. And he goes through this discussion very nicely. In particular, of course, the Easter Islands cut down all their trees, and then they were surprised that they would perish. Now, are we doing a similar thing? Of course we are, right? But Diamond is saying that we have an opportunity to learn from these mistakes. We have means of instant communication. I'm doing this right now with you, right? And that's, of course, an opportunity which past societies have not enjoyed. So my view is, so young people, and I put them within quotation marks, from my vantage point, of course, everybody is young, right? So even if you are in the 60s, then you probably, most of them in my experience, have already gone into retirement and have, as engineers now, I mean, and have gone on to more worthwhile hobbies, and they don't think about these problems anymore. The ones who are in their 40s and 50s, in the peak of their careers, are very busy, right, and are not allowed to work on such problems most of the time in the companies they're working in. And the young engineers, the ones that are 20 and 30, they, of course, should have the greatest interest in this. And in particular, they should have an interest to try to get started on what I call an energy Apollo project, right? Modeled after the original Apollo project. So in order to summarize, and I'm over time a little bit, but I can summarize it like this. The energy ship concept, in my view, requires the combination only of well-established technologies. That, to me, is a very, very important point. Sailing ships, turbines, electrolyzers, hydrogen compression, liquefaction, all these things are developed technologies. They, of course, can be developed further. They can be optimized, but they are available. And so we can build on that, and we can do this relatively quickly, in my opinion. And we should not forget that we need to get this done in time before it's too late, because of the phenomenon of irreversible climate change. And we have an abundant supply of energy in the winds over the ocean. So I thank you very much for your attention. I will be very happy to answer any questions. Thank you very much.
Thank you very much, Professor. Now, I think audience can ask question. They can unmute themselves and ask question, or they can use the chat window. They can ask question.
Max, Torsten Franzen here. I was wondering, how much do you estimate that you will actually get out of one ship, and how long does that ship have to be on out on the ocean, and where would you have your tankers, etc.? Have you put any thoughts into these items?
Yes, indeed, and I prepared a few more slides so that I can answer some of these questions. So here, for instance, you of course have the whole sequence, right? You go through, you have to take in salt water, you have to desalinate it, you have to go through electrolysis, and different types of electrolyzers are available. You have to compress it, and how much will you generate per week or per day or per month? My view is, and I think I have this here, how much hydrogen can actually come out. These are the numbers, right? So how much can you get out of the electrolyzer? How much power do you need? So for instance, in this case, we figured that for a 1 megawatt ship running for 1 week, you would get 2,900 kilograms of hydrogen. So what would you do with that? My view is there are a number of ways to do this. I would think you would, within a few days, you would have to come to a what I would call a hydrogen refinery ship, a large ship, which is somewhere close to the autonomous sailing ships, to the energy ships. Unload your compressed hydrogen tanks, liquefy the hydrogen, and in separate tankers bring the hydrogen back to the coast. And then, of course, do with hydrogen what I already indicated. Or you could come directly to the coast and unload. Another possibility is to bring all these hydrogen tanks back to the coast directly. These are possibilities. The logistics of that, I might mention, we have analyzed, and by we I mean my colleagues at the University of Nantes, and I have been a course of that. We have published a paper, and they have published more on that. They have analyzed that logistics problem in considerable detail. So that would be my answer. Obviously, I cannot go through these details here, but we have heard about this problem. It's a very important problem, of course. That's the other reason why the energy idea has not caught on all that rapidly. But again, I see no real technical problem, right? But naturally, all this needs to be demonstrated, and that is why I say we have to start small. We have to get experience with small boats. This is why I'm now trying to get funding for a small boat. My French colleagues have already succeeded in getting funding for such a small boat, and they've put out some numbers. They have a publication coming out on that very shortly. I don't know about the Japanese work in detail. Clearly, when you get some actual numbers rather than just analysis, where everybody, of course, is saying, well, how good is your analysis? Good enough, right? You ultimately have to demonstrate all this in terms of hardware and build up from there. My view is, let us not forget how aeronautical engineering got started. The Wright brothers built a very flimsy kind of a thing which could fly only the length of a football field. And would they have imagined that you can fly 500 people from New York to Sydney later on? Right? Now, all these things take a certain development time. and you have to start small and get experience.
Yeah, how you're here mentioning on this slide here, you're mentioning 3 metric tons of hydrogen.
Yeah.
How much would that, to what extent would that help us, so to speak? I mean, how much is that compared to what we would need for the Tesla cars or whatever?
Well,
I mean, if you,
a Tesla battery is about 80 to 100 kilowatt hours. And now you say, let's go back to this one possibility, which is the one which I first would like to examine. And that is have such a small boat operate close to the coast. And if that boat has, and now you pick a number, eh? I said it can generate 13 kilowatt. Maybe a bigger one could generate 20 kilowatt. Though you operate it now for a few hours and you got your 100 kilowatt hours, right? That is your battery. And you bring that battery back. Now it depends on the size of the ship and how many batteries you can load on your ship. And you bring them back and you put that into your Tesla cars or smaller ones, right? Smaller electric vehicles typically have something like 20 to 40 kilowatt hour batteries. So you could provide, and maybe that is a possibility for commercial applicability, right? That somebody who wants to operate a small boat, relatively small boat, can have this boat operate during the night autonomously, brings it back in the morning, unloads the battery, brings it to the customer who has an electric vehicle and says, I charge you so and so much. Every day I bring you your battery, and you don't need to worry about recharging it using energy, which in many cases, of course, comes from carbon emitting power plants. Right? So there ought to be an incentive to provide people with emission-free power in the form of batteries, electric batteries. Or later on, of course, similarly with hydrogen. Right? And that gives you the problem of, or the question, how do you distribute the hydrogen? Well, we have hydrogen pipelines. We have pipelines, natural gas pipelines, and so you can put the hydrogen into your natural gas pipelines. Not fully at the moment, as I understand it, that cannot be done, only a certain amount. And you extract the hydrogen on the other end and then make it available. Right? So there are a number of, or you do this in trucks, you deliver it in trucks. So these are the possibilities how to use them. Right? But I emphasize that this is not something that can just be done with a few ships. That requires a large number of ships and all the infrastructure that goes with it, right?
well, there is of course one advantage, because here in Sweden the delays of installing wind power is mainly based upon the fact that the citizens do not want to have them in their backyard.
Exactly.
And then you do not want to have it close to shore either, because that's the view,
Yes.
and that will destroy tourism, etc.
Well, in California, the permitting process will take 2 years in order to get this even allowed to start construction, right?
Well, here in Sweden, it's there have been cases of 10
Even
to
longer,
15 years. So that,
Yeah.
yeah. Mm.
So,
Okay, thank you. Mm.
I don't quite understand. I don't have a good sound. I'm afraid I cannot understand you. Can somebody come in and
I couldn't hear it either.
no?
Very, very low volume.
Yeah.
Might the speaker perhaps write it in the chat?
So seems no question for this. So Iresha,
I could make a few more remarks if I have a little bit of time. If you want to give me that time.
sure, Professor. Yes.
How dangerous is the situation we are in? I would like to give you an example. All of you know that we lost 2 space shuttles, one in 1986 and one in 2003. Did that come as a complete surprise? Or should we have known about that? And should we have done something about that? The reason I'm giving you this example is we are in a spaceship. And we have plenty of indication that there's something wrong with our spaceship. Just as there was plenty of indication that there was something wrong with the space shuttles. So what everybody ought to realize is that you should not ignore or downplay the signals that are sent out by, in this case, of course, it was a man-made vehicle, right? The space shuttle. Our spaceship we have been given, right? But we should take care of it, and it is sending out the signals. So what was the attitude here? And I refer you in particular to the investigation which was conducted by a famous physicist, Nobel Prize winner, Feynman, in this book, which he called "What Do You Care What Other People Think?" I think it is a very instructive reading. I recommend it to everyone to do that. Now, NASA said, well, we estimate the probability of failure is 1 in 100,000. That meant that the shuttle could fly every day for 300 years. Right? This is the kind of numbers they were putting out. And they felt that, yes, there were puffs coming out of the solid rocket boosters. And that was considered kind of normal. So we got away with that for, I guess it was 34 times. And it totally failed on the 35th time. That was irreversible. That was a rapid change. Now, what kind of attitude was that? And so that is what Feynman is saying. Let us make recommendations to ensure that NASA officials deal in a world of reality, understanding technological weaknesses and imperfections well enough to be actively trying to eliminate them. For a successful technology, reality must take precedence over public relations. And that is the important statement here. For nature cannot be fooled. We cannot go on like this much longer. We need to take care of spaceship Earth. And the same thing happened for Columbia, right? No lesson was learned. And we paid the price, right? And so that is basically what I would like to get across. in particular for the young people, let us not underestimate the danger. And you will have another 60 or 80 years in front of you, right? And you can see the signs, and something needs to be done. And my point is, and that is what I would really like to leave you with, is as engineers, we have here a chance to develop a new technology. Well, I also said it's not really a new technology. It is an available technology which can be refined, which can be further developed. And the other interesting thing for me is the early enthusiasts in aeronautics, think of the Wright brothers and the many others, right, who were building first airplanes in their backyards. They were enthusiastic and they started experimenting with this. Look at these, what I would call interesting air-sea interface vehicles. Huh? You can do that actually yourself. Huh? This does not require a big project. This does not have to be millions and millions of dollars to get started. That can be started at the ground level. That can be started essentially by young engineers to refine and to ask the question, how does this vehicle have to look in order to get the optimum amount of power out of it? In other words, how do I have to build it in order to minimize the drag and to maximize the lift with which I can propel this vehicle? And this can be done relatively quickly and with relatively small amounts of money. So here you have a chance to individually, many of you can get started in doing this and can start to attract attention to this, so that the older ones will become a little bit more, shall we say, active. Right? And the older ones have the attitudes that it requires so much money, and it is so complicated and so difficult that it may require new innovations and things like that. That is a misconception in my view, and that is mostly the message I would like to get across.
Yes, Lekha, I think Professor concluded the lecture, so can you do
Yes. Thank you, Tushar. Actually, it is indeed a great honor for me to thank you, Professor Max. Agree with you, the nature cannot be fooled, yes. So thank you very much, Professor Max Platzer. That was an interesting and really, really informative speech. So I wish to thank you first for giving us this valuable information. We have had the opportunity actually earlier to listen to about floating structures which in offshore, which generating power using solar energy. Now today we listen to generating power using offshore wind, and it's already there, and we all know that solar energy is one form of energy income which we can afford to live. And wind is there again, and hopefully it's in the offshore, so wave energy is also there abundantly. So we can, I mean, combine all these things and see how we can proceed to the future, so that our young engineers will look into all these sources which are available abundantly and find a solution to the wicked problem, as you say. So it's to go into the carbon neutral future or in a carbon neutral environment. Thank you, Professor, again. It's really, really a nice talk. And next, I would like to thank Professor Thorsten, who gave us this opportunity actually to listen to Professor Max. And then I like to thank the EUSL-Energy project and the Open University and the Sri Lanka Advancement of Science Section C. which gave us the opportunity to have this talk series, webinar series. And then last but not least, to the audience who were here to listening to Professor Max. Thank you very much, Professor, again.
Thank you very much again. It was a great honor for me. Thank you very much.
Yeah.
Thank you, Professor.
Thank you.